Satellite.
This is a satellite. If you look up at the night sky and see a tiny star moving steadily in a straight line, you are probably looking at one of these.
Fundamentally, it is just a very expensive floating antenna. But why go through the trouble of putting it in space instead of just building taller towers on the ground? Because planets are round. Radio and internet signals travel in straight lines. A tower on Earth can only broadcast so far before the physical curvature of the planet gets in the way and blocks the signal. If you want to beam a message across an entire ocean or track a global storm, you need an antenna so ridiculously high up that it can look down on half the globe at once. So we put them in space to be our dedicated orbital workers.
A lot of people think satellites float simply because there is zero gravity in space. That is entirely wrong. At the altitude where these machines operate, Earth's gravity is still incredibly strong. It is pulling on that metal box almost as hard as it pulls on you standing on the ground.
If you were to launch a rocket straight up into space, drop a satellite, and just leave it there, it would not float. It would immediately plummet straight back down and crash into the ocean.
So how do engineers keep it up there for 15 years? The solution is not pushing it up. The solution is throwing it sideways. When a rocket launches a satellite, it turns horizontally and accelerates to an insane speed, usually around 28,000 kilometers per hour. Because it is moving sideways so incredibly fast, as Earth's gravity pulls it down, the actual curved surface of the Earth falls away beneath it. It is perpetually falling, but it is moving so fast that it constantly misses the ground. And because there is no air resistance in the vacuum of space to slow it down, it never stops. To keep the computers inside alive, they attach giant solar panels so it can feed on the sun indefinitely.
But this brilliant solution comes with a brutal compromise. It has absolutely no freedom. Once it is thrown into that perfect balance of falling and missing, it is completely trapped. It cannot steer. It cannot suddenly decide to fly to the moon or visit another planet. It is a permanent prisoner of its own momentum. Its ultimate fate is to spin around our planet in total silence for decades, until its internal parts finally break down, turning it into a very fast, very useless piece of space trash.
Space capsule. This is a space capsule. If satellites are built to stay up, this thing is built to come down. It is essentially a pressurized, heavily armored metal safe. While it does have some tiny thrusters to maneuver in the vacuum of space, its entire existence is defined by one terrifying, highly specific job: bringing soft, squishy humans back to the surface of the Earth without turning them into ash.
Coming back from space is not like slowly descending in a hot air balloon. Remember how fast satellites have to move to stay in orbit? Over 28,000 kilometers per hour. When it is time to go home, the astronauts have to plow into Earth's atmosphere at that exact same insane speed. At that velocity, the air in front of the spacecraft cannot get out of the way fast enough. The air gets compressed so violently that it instantly turns into searing hot plasma, reaching temperatures hotter than the surface of the sun. If engineers designed the spacecraft to be sleek, sharp, and aerodynamic like a fighter jet, the sharp edges would absorb all that heat, melt instantly, and incinerate everyone inside. So aerospace engineers designed the bottom of the capsule to be completely flat, wide, and blunt. Instead of smoothly slicing through the wind, the capsule violently punches the atmosphere. This blunt shape forces the air to pile up in front of it, creating a massive, invisible shockwave. The sheer genius of this design is that the shockwave acts as a protective bubble. It forces the superheated plasma to flow around and away from the actual metal hull of the ship, keeping the astronauts safely insulated from the firestorm outside. But because it is shaped like a blunt cone, it has the aerodynamic flying capabilities of a heavy rock. It cannot glide, it cannot steer toward a runway. Once it enters the atmosphere, the astronauts have absolutely no control over where they are going. They are essentially locked inside a falling metal box, forced to just drop from the sky and passively pray that their parachutes open at the very last second before they hit the ocean. Space Shuttle. This is the Space Shuttle. This is arguably the most famous spacecraft ever created. Its main purpose was to be the ultimate reusable delivery truck for low Earth orbit. It was designed to carry extremely heavy cargo like satellites or pieces of the space station, deploy them in the vacuum of space, and then return its crew safely to a normal concrete runway, just like a commercial airliner. But Space Shuttle is a massive contradiction in physics. It is a vehicle forced to operate in two completely different environments that demand two completely different shapes. In the vacuum of space, aerodynamic wings are completely useless because there is no air to fly through. However, to land on a runway back on Earth, wings are absolutely mandatory. And just like the space capsule, it still has to survive smashing into the atmosphere at 28,000 kilometers per hour, which creates a wall of scorching, vehicle-melting plasma.
To solve this impossible contradiction, they gave it large delta wings and a tail so it could steer through the air. But to stop those airplane parts from melting during re-entry, they meticulously glued over 24,000 individual highly fragile ceramic tiles across its entire belly. These black tiles acted as a thermal sponge, absorbing the extreme heat so the aluminum airframe inside wouldn't turn into liquid. But trying to be good at two things made it terribly inefficient at both. For the entire duration it is floating in space, those massive wings are just useless dead weight that cost millions of dollars in rocket fuel to carry up there. And when it returns to Earth, it is a terrible airplane. Its main engines only work in space, meaning it has to glide back down entirely unpowered. It essentially falls out of the sky like a winged brick, dropping 20 times faster than a normal commercial jet. The pilots have exactly one chance to hit the runway. If they miss, there are no engines to turn around and try again.
Space probe.
This is a space probe. Because the word probe sounds like a small drone, people often imagine them to be the size of a microwave. That is a massive misconception. These things are absolute behemoths. Many of them are the size of a school bus and weigh several tons. They are fully autonomous robotic laboratories. But why do we launch them millions of miles into the dark? Because telescopes on Earth can only see so much. To truly understand our solar system, we have to physically send sensors there. A probe's job is to fly directly through the rings of Saturn, taste the toxic clouds of gas giants, and take extreme close-up photos of alien moons. And unlike satellites that stay close to Earth, probes are built for a one-way trip. Their sole purpose is to leave home and never come back.
The problem with exploring the outer solar system is that space is unimaginably vast, incredibly dark, and violently cold. When a spacecraft travels out past Mars toward Jupiter and beyond, the sun becomes nothing more than a slightly bright star in the distance. This means giant solar panels, the standard way spacecraft get their power, become completely useless. Furthermore, because they are millions of miles away, there is no mechanic who can fly out and fix a broken wire. If a single critical component freezes or snaps in the dark, a multi-billion-dollar mission is instantly dead.
To survive this freezing exile, engineers cannot rely on the sun. Instead, they give the probe its own internal nuclear battery. It uses the natural decaying heat of radioactive plutonium to generate a steady supply of electricity. This nuclear heart keeps the spacecraft warm and its computers running in the freezing void for decades without needing a single recharge. To solve the problem of breaking down, engineers build every system with paranoid redundancy. If one computer fails, a backup wakes up. If a heater dies, another one turns on.
But once a probe is launched, there is no return ticket. And because it travels so ridiculously far away, communication is agonizingly slow. Sending a simple command to take a picture can take hours to reach it, and you have to wait hours just to get a beep back.
Rover.
This is a rover. Because it has 6 wheels and a camera on top, it is incredibly easy to mistake it for a giant remote-controlled car. But it is not a car at all. It is a multi-billion-dollar robotic chemistry lab on wheels. Its mission is to land on an alien world, like Mars, drive across uncharted rocky deserts, shoot lasers at rocks, drill into the dirt, and hunt for the chemical signatures of ancient life. It is the ultimate off-road vehicle, designed to operate on a planet where humanity has never even set foot.
But Rover has an absolute isolation combined with a massive communication delay. Earth and Mars are so far apart that a radio signal traveling at the speed of light can take up to 20 minutes just to get there. Because of this lag, you cannot drive it live with a joystick. If a human operator on Earth sees the rover heading toward a cliff on their monitor and hits the brakes, the rover actually fell off that cliff 20 minutes ago. And the golden rule of Mars is there are no tow trucks. If the rover flips over, the mission is instantly, permanently dead.
To stop the rover from ever tipping over, engineers designed an incredibly flexible suspension system. Rather than absorbing bumps like a normal car, it continuously bends and reshapes itself to match the terrain, mechanically forcing all 6 wheels to stay in contact with the ground whenever possible.
And since real-time driving is impossible, they let the rover make its own way, constantly scanning the terrain and cautiously crawling forward on its own.
But this obsession with safety comes at a cost. Every movement is deliberate, every decision carefully calculated. As a result, this multi-billion-dollar machine crawls across Mars at just 0.1 miles per hour, slower than a garden turtle. A distance you could casually walk in 5 minutes may take the rover several days to complete.
Space station.
This is a space station. Unlike the other spacecrafts, it doesn't fly anywhere, and it doesn't explore the unknown. It's just a permanent orbital house. Its only real job is to keep a bunch of humans alive in a vacuum for months at a time, so they can do zero-gravity science experiments. It's basically the most expensive floating metal skyscraper humanity has ever built.
But here's the problem. Building a house in space is a logistical nightmare.
It's roughly the size of a football field, far too large for any rocket to launch in a single piece. And even once it's in orbit, another problem begins. With no air to carry heat away, all the heat from the computers, life support systems, and astronauts builds up inside. And without a way to remove it, the station would slowly bake its own crew alive.
The solution was surprisingly simple in concept. Build it like a giant Lego set in space, one module at a time. And to keep it from overheating, they equipped it with massive radiators that continuously dump excess heat into space.
But this engineering marvel comes with an enormous price tag. Every kilogram of food, water, equipment, and scientific experiments has to be launched from Earth. Even replacing a single broken component can require an entire rocket launch, making the station one of the most expensive machines humanity has ever built.